Today we're going to continue with chemical equilibrium and focus on the chemical equilibrium expression and the equilibrium constant. So the equilibrium constant is just a number, but what happens in equilibrium is no matter what the starting composition, meaning it doesn't matter how much of each reactant, or we have some combination of reactants and products, when it reaches equilibrium, there's some value that we're going to reach when we take the ratio of the products and reactants. We call this constant chemical equilibrium, or KEQ. This K is the equilibrium constant. The ratio is always products over reactants. We're going to look on the next slide a little bit more into that, but the key is to remember products are going to be in the numerator, reactants in the denominator. We'll pull out a laser pointer for that. So KEQ is kind of our standard. You may see KC or just K. Some of these are carryovers from older conventions, but just recognize for us these are all going to mean the exactly same thing. And keep in mind this K is just a some number. It can be 0.56, 11.3, 2.7 times 10 to the minus 18, some number. But this value is going to be different for every chemical reaction, and it will be different for temperature. We're going to look at that a little bit, but most of the time the temperature is not going to be a big deal for us. Okay, for a general reaction, so we said it's products over reactants. So we see P and Q here. So this looks a little bit confusing at first, but let's break it down. So again, starting with products. Remember, everything to the right is products, no matter if we start with P and Q or whatever. It's how we write the equation. So we have to have an equation written, or actually have the equilibrium expression to know how this K relates. So remember, these brackets are concentrations. So what we say, it's the concentration of each product. In this case, the concentration of P raised to the power of whatever its coefficient is in the balanced chemical equation. Okay, so we have concentration of P raised to the coefficient times the concentration of Q raised to its coefficient. Again, the products are on top. We do the same thing on the bottom. So it's the concentration of A raised to its coefficient times the concentration of B raised to its coefficient. Okay. One thing to note, we see that these are aqueous and gases here. Pure solids and liquids are not included in the equilibrium expression. We don't have any here, but let's draw something out and just give you a quick idea of what we mean by that. So when we look at, we'll just call it A, and that's a solid. All right, we put a piece of metal or something, or just some powder into some aqueous solution, whether that's an acid or not, and we get C, some gas produced, and then D, some other aqueous. And let's assume these, well, actually let's put a coefficient in here. We'll say it was 2C. Okay, so when we write the equilibrium expression for this, right, we still have K. Okay. Again, it's products. Right, this is a gas and aqueous, so those are going to be included. I seem to be writing on a bit of a slant, but we have the concentration of C to the second power, or squared, times the concentration of D. It's to the first power, so we just leave it as the implied 1. We don't write the 1. Now, since A is a solid, we do not include that in our equilibrium expression. So it's just over the concentration of B. Again, it's to the first power. So this is our final equilibrium expression for that reaction. Okay, I just want to come back and talk about the K value and what it means that it's a constant. So we're using a very simple equation. which will make our lives much easier in this example. Again, it's not about solving these problems, it's about understanding what this all means. It's simple. We have one reactant, one product. The ratios, they're just a 1 here and a 1 here. So it's going to make our math really, really easy. And so what we're saying is if we start with something like 3 molar A, right, we know again that the concentration of B is going to end up being 2 and the concentration of 1 or A is going to end up being 1 because that gets us to 2.0. Again, the math here is pretty easy because these have to add up to the 3. So 2 plus 1 gives us the 3 molar. Again, because we have this simplified equation here. The math gets much, much more difficult as you go along, but not for us. That is more of AP level. Okay, so what would this look like if we had a different amount of A? Well, if we had 6 molar A, right? Again, we know this is going to have to be 4 molar for B and 2 molar for A. Once again, it comes out to 2.0. So we see it doesn't really matter what we start with. This ratio has to come out to be the same. Likewise, we could start with 6 molar B. Right? So we started off with a different amount. Okay? And we would get, once again, the same as we just got, starting with 6 molar A. And we get, again, 2.0. Now, what happens if we go with, I don't know, 12 molar B? Okay. Well, we have to add up to 12 and get 2.0. So we would have 8 molar of B and 4 molar of A to give us 2.0. Notice how these final concentrations are different depending on what we start with, but it doesn't matter if we start with B or start with A. This value of K, or that ratio, always has to be the same. And so that's what the beauty of K is, and the importance of K is to get us that information. Once again, the math gets very complicated. We're not going to solve it. And so you can't always just as easily I did here. We used numbers that would work out well for us in a simplified equation. Okay, take a moment and practice this problem, writing the equilibrium expression for this given reaction. Maybe hit pause. Okay, so let's look at the answer. Once again, we're going to start with the products in the numerator, which is NH3 raised to the second power. And maybe we can get the slide to change and bring the answer up. There we go. So we have NH3. Remember, we do need the brackets. These brackets are telling us this is the molarity of NH3, again raised to the second power, which is the coefficient here in the equation. N2 and H2 are reactants, so they're going to go in the denominator. N2 is just first power, or the coefficient is 1, so we just leave it as blank, the implied one. H2 is to the third power. Hopefully you got that. They're really not too difficult once you've got the understanding. You remember products on the numerator, reactants in the denominator. The one tricky thing again is that we don't include solids or liquids. So if this is an S or L, we just ignore them and write the other things in our equilibrium expression. So just a little summary. So KQ is the molarities. Again, those brackets mean molarities. So make sure when you plug numbers in, if you plug numbers in, we're looking at molarities. The K value has no units, so there isn't like molarity or stuff. It's just a unitless measurement. The reasons for that are a little bit complicated, so we will not be going over those. And again, for the, I don't know, many times we've said products over reactants. Since K is just a number, we want to look at what that actually means. Right, so I'm going to bring a pen up here so we can draw here. So first off, magnitude of equilibrium means, what does that number mean when it's big or small? What does that tell us about the ratio? Okay. Well, simply put, right, we're dealing with a fraction. Right? So K equals products over reactants, right? Okay. So yeah, there's powers involved and stuff that we have to deal with, but in general, this can still just give us the basic idea, right? If products is really big and the reactants are really small, and they don't even have to be that small, but right, this is going to give us a big K value. Right? So if the products are big, it means we got a lot more product than reactants. So the bigger the K value, the more products we are going to produce. Right? However, if we do the other side and say we got small amount of product versus a large amount big reactants, that means our K is going to be small. So once again, if we have a large number of reactants left or at the end, a small number of products, that means our K value is small. Okay? So we use this kind of phrasing here. So if K, this simply means much bigger than 1. So what much bigger is, it's not really a cutoff, but even a number like 10 would be considered probably in most situations much bigger than 1. So a large K value, we call it product dominant, or just like up here, our big K means we have a lot of product. Another terminology we use is lies to the right. That doesn't mean physically things move to the right in a container or something. It simply means looking at the equation, reactants going to products in equilibrium. Products are on the right side. So when we say lies to the right, that means this is big and this is small. That's all lies to the right means. We're going to continue this terminology in the next section. So we want to make sure we understand that. Likewise, this means much less than 1. Maybe that's 0.1. So don't really have an exact cutoff, but that's kind of where we start. So again, if it's small, that means coming back up here that there must be a small amount of product compared to the amount of reactants. And again, it's all relative because you might start off with very small amounts of both of them, but at the end, right, it's the comparison of how much you have, or the ratio of one to the other. And once again, we're using the phrase lies to the, in this case, left, because the left side of the reaction is where the reactants are. The other scenario about this is, some of you may have already been thinking, it's like, well, if we have an equilibrium expression, this is like the first one we started off with, right? Can't I write that another way? Right? If I just flip it around, doesn't that chemically mean the same thing? And the answer is yes. Okay. So the molecules don't know what way you wrote it, but if we flip it around, some of you are already seeing, well, this number has to change because the equilibrium expression wouldn't be the same because it's always products over reactants. So once again, to iterate, to write an equilibrium expression, we need to have a chemical reaction written out. Okay? Or if we're given an equilibrium expression, we can write the specific reaction for that. So in this scenario, and at whatever temperature this is, our value of K is 0.212. Okay? So what happens if we do write it the other way? This way I wrote up here. Well, if we flip it around, of course now the equilibrium expression is this. It's N2O4 over NO2 to the second power. So really we're just flipping over the fraction, which means we're just flipping over the K value. So it's 1 over 0.212, and so it's 4.72. And so, as we say down here, the equilibrium constant for reaction in one direction is the reciprocal of the equilibrium constant in the opposite direction, or just 1 over whatever K was in the previous reaction. Okay, so let's just look at one really sort of easy, brief other example. Say A goes to B, they're both gases, so they're both part of our equilibrium expression. And let's just say K at whatever temperature this equals, well, let's just call it 2. Okay. So if we were to write this equation a different way, remember this doesn't change chemistry at all. Right? These things don't know how you're writing the equation. The system, the reaction is just going to occur. So K for this is just then 1 over 2, and of course that would be 0.5. Alright, so that's it for equilibrium expression, equilibrium constant, and what that K value means. As far as solving these problems mathematically, we will not be doing a lot of that. We may just plug some values in, given some molarities, plug them into the equilibrium expression, and calculate K, but there will not be complicated math.
Have you seen Junior's grades?